Based on this information, what do you think is going to bind with what? So, this is what is going to happen in these different strands. So, this is, say, strand 1, and this is strand 2. If you have this adenine, C coming from this side. So these two polynucleotide strands are going to interact only through hydrogen bonds between the A and the T's and the C's and the G's. And this can go on like millions of times. These alternate factors, so you have A, C, then maybe another C or G or whatever. This thing can go on, and that is the code. That is the password. Like this sequence of these nucleobases is the code. Because once you fix the code on this side, the other side is also fixed, because it will only bind with, this is not going to bind with C or G or even another A. This is going to bind with the T. So this is the code. Okay? These are the 2 hydrogen bonds and the 3 hydrogen bonds. Okay? So DNA is important, it is complicated, but it is, once you kind of break it down into individual parts, it becomes more tractable, right? So it has 2 strands. Each strand is called is called a nucleotide. That nucleotide is made up of a nucleoside plus the phosphate. The nucleoside is made up of the sugar and the base. We have 2 different kinds of bases, pyrimidines and the purines. We have A, adenine and guanine as the 2 purines. These are the pyrimidines, right? So there are different kinds of really interesting chemistry that happens in these structures, but for our purposes, just let's keep at that. Now, the difference between DNA and RNA is what? It's a single strand, and it is not double strand. Yeah. So the bases that we have is cytosine, guanine, adenine and uracil. So we don't have a thymine in DNA. In RNA. Right? So you have C and uracil, and we have adenine and the guanine. And this is single stranded. Okay? With this, let's conclude this discussion on the biomolecules. It took a long time, but it was good to understand all these. I'll just quickly, in the 5 minutes that I have, right? So let's think about the solvent in which these reactions are happening. The solvent that we have is water. This is the solvent. There are unique properties of water that makes life possible. What are those unique properties? This is a polar molecule, right? It has a dipole moment. So this dissolves polar compounds. This has a high specific heat capacity. That means it takes a huge amount of energy to raise the temperature of water. That is why when you drink water from wells or deep underground wells, you will see that they are cooler during the summer and warmer during the winter. Why? Because it is very difficult to change the temperature of water. This also has a unique property, and we saw that in the phase diagrams a little bit, that ice is less dense than water, or the maximum density of water is 1 gram per cc at 4 degrees Celsius, which is not its freezing point. That means when you have a beaker of water that is undergoing cooling, so say you have started to cool from 10 degrees Celsius. So you started cooling from the top. So let's imagine this is a lake and the environment in here is colder. So this gets to 9 degrees Celsius, becomes denser, goes here. And the water that is not at 9 degrees Celsius or 10 degrees Celsius goes up. So as it is going from 9, 10 to 9 to 8, it is becoming colder and more dense. So it comes down and the less dense water comes out. But this process stops at 4 degrees Celsius. At 4 degrees Celsius, what happens is everything will become 4 degrees Celsius, and then if you make this water 3 degrees Celsius, the top water 3 degrees Celsius, this is not going to come down because it is not dense. If the 3 degrees Celsius water is less dense than the 4 degrees Celsius, will it sink? If it is less dense, it will not sink. So 3 degrees stays on the top, it doesn't sink. Becomes 2 degrees, doesn't sink. Becomes 1 degree, doesn't sink. Becomes 0 degrees Celsius, doesn't sink. Then starts to form ice. And it stays ice in the top, allowing life to sustain. Because we need liquid water for sustenance of life. Why do we need liquid phase? Why can't life just take vapor or solid?
Transport different things.
The gas can transport it faster. So what is the problem? Can I have water vapor? Is that sweet spot in between. So if you have, you need movement, you need transport, right? But the second thing is, you need a media. Vapor is not able to give you that media. Ice, on the other thing, can give you that structure, but it will not allow movement. So that is why liquid water is important. And the dipole moment, the high specific heat capacity, and the ice less dense than water. These four, plus add the hydrogen bonding capacity of water, is making water one of the best solvents that we know that can sustain life. Now, are there other solvents that can do it? So methane, ethane, those solvents that are there on Titan, not that likely, because they are non-polar. Ammonia comes a little close, because ammonia will have a dipole moment, right? It will dissolve materials. But the thing is, ammonia has a really low boiling point. It does not have a high boiling point like water. That is a problem. But any planet that has cold temperatures that can stabilize liquid ammonia might be able to do some neat little tricks to support life. But you need that liquid ammonia. But methane cannot do it. H2SO4 can also do it. HF can also do it. So any of these solvents that can stay as liquid but also need to have like this dipole moment. So like staying as liquid with a high boiling point and with this high dipole moment is kind of like very important. Methane doesn't check the bell. So like check the box. Yeah? HAF, H2SO4, they will have other problems because they can donate H+. They are very acidic. So there is a limit to what life can sustain. Actually, it's life as we know it. The other thing is when you have very concentrated solutions, the water activity becomes low. We'll deal with water activity. Maybe you already know, but we'll deal with water activity. So there's a very narrow window in which, like if the water activity gets below a certain point, when you get more and more concentrated, life becomes difficult. So in neutral, in a pure water, life can say exist. The activity of water in pure water is 1. But if you make it more concentrated, the activity decreases, say 0.9. Make it more concentrated, 0.8. So what is that limit below which life will not be sustainable? So we will look into these things in the next class. Okay? All right.